Okay, the point of this video is to supplement our Chapter 4 lecture from in class, where we covered all the concepts of force from Chapter 4. We didn't get a chance to do some problems, so I'm going to go through this hopefully as quickly as I can, so that you can get straight into the problems. So here's a list of tips. I'll do one generic example and 3 specific examples. First thing you always want to do is draw a force diagram. So a force diagram consists of a box. You label what the object is, mass equals whatever it is, and you can start setting up your different forces. So say we have one force this way, just call it F1, and then we have another force this way, say F2, and suppose we have a third force backward, F3. For now we'll ignore up and down forces because this is all about motion in one dimension. So just say the object's moving side to side. Now we set up our Fnet equals ma equation. So this is always true. So if you've drawn all the forces on the force diagram, you can start by writing Fnet equals ma. And now in place of Fnet, you can actually fill in all the forces. So if we choose to the right as positive and to the left as negative, which is a pretty good convention, then the net force is F1 positive plus F2 positive. These are both positive because they're pointing toward the right or the positive direction. And then minus F3, or plus a negative because F3 is in the negative direction, equals ma. So here we've set up, this is what I call setting up your Fnet equals ma equation. Now you can solve for what you need. If we knew the acceleration and 2 of the forces, we could find out the third one. If we knew all 3 forces, we could find out the acceleration, or any combination thereof. So it's important to set up this equation for each and every problem, even when they seem really easy, because you'll build the good habit and you'll be able to find out what you're missing. Second thing I want to point out is a lot of problems, they tell you all the information about force, they allow you to draw a great force diagram, and then you calculate the acceleration. So sometimes that's your final answer, acceleration equals blah, but a lot of times you then need to use that acceleration value and move into the motion part of the problem. This is where you put VI, VF, acceleration, distance, and time. So the problem will also give you 2 out of these, and then you use the force diagram to get the acceleration. So you'll have, say, acceleration and 2 others, and then you can find out some motion stuff. So if the problem is asking you about motion, like how fast or how far or how much time something is taking, you often use the force diagram to first get the acceleration as part 1, and then you use the acceleration to find out the motion in part 2. Let's apply this strategy to a couple of example problems. First one, a 3 kilogram plant is sitting on a balcony window at rest. Draw a force diagram and find the value of all forces. So we have a 3 kilogram plant. We draw it in a box. It's got the force of gravity downward, force of gravity on plant, if I'm trying to be pedantic here and really show my work, gravity on plant. And the equation for the force of gravity on plant is mg, because we're on Earth's surface. And I know the mass is 3 kilograms. I know gravity is 9.8 newtons per kilogram. 3 times 9.8 is 29.4 newtons. Okay? The force of gravity is 29.4 newtons downward. And because I know that the object is at rest, it means its acceleration is 0, which means its force net, or total, is 0. And if its total force is 0, then there must be an upward force that's exactly equal and opposite to the downward force. So this is the force of the, say, balcony on the plant, holding it up. And that, I don't have to do any math, and there isn't any math to do. I can just say that that has to be 29.4 newtons, and I know it has to be that much because it's equal and opposite to gravity. So this is my force diagram with a value of both forces. Now suppose we knock this plant off the window, draw a force diagram. So it still has gravity acting on it. I'll just use Fg as shorthand. And this is the same force of gravity because it's the same mass. So whether it's falling or whether it's at rest, the force of gravity is the same, 29.4 newtons. And now because it's no longer touching anything, it's not being supported, there is no upward force. So this is the complete force diagram. We might label the object again 3 kilograms. But this is the complete force diagram. There's no other forces. There's nothing else happening. It's just accelerating downward. So if we were to write our Fnet equation, Fnet equals ma, the only force on here is gravity. Let me write mg equals ma. How cool is this? Now, mathematically, m cancels out, and we can see that the acceleration is equal to g, 9.8, because it's in free fall, so it's going to accelerate downward. Alright, next example. Here we go. A 30,000 kilogram rocket ignites its thrusters, which exert a 450,000 Newton upward force. Find the acceleration of the rocket. So, first thing, do not just jump to the conclusion and try to plug into an equation. Draw your force diagram. So we have a 30,000 kilogram rocket. It's providing an upward thrust. Force of, say, the engine is 450,000 newtons. We also have the force of gravity. This arrow should be smaller than this arrow because otherwise it wouldn't launch. The force of gravity is mg, which is 30,000 times 9.8, which is, let me grab a calculator here, 30,000 times 9.8, 294,000 newtons. So at this point you've got all the forces labeled, and you have to ask yourself, is there a normal force supporting the rocket? Not really, because as soon as it fires its engines, it's pushing off the ground and it's no longer in contact. Before the engine got turned on, of course, there would have been a normal force upward, equal and opposite. But now that it's launched, as soon as it leaves the ground, even a millimeter, it's only the engine force acting on it, not the normal force as soon as it leaves contact. So we can set up our Fnet equation. Fnet equals ma. I have an upward force, F engine, minus the downward force, force of gravity, equals ma. And now to solve for a, I'm going to divide both sides by m. So I can cross the m out. And now I can do F engine, which is 450, so I'm going over here. 450,000 minus 294,000 divided by the mass, which is 30,000, equals the acceleration. And we'll calculate this out. 450 minus 294 equals, divided by 30 equals 5.2. 5.2 meters per second squared. So that's about a half a g that this thing is accelerating at, which is quite rapidly, probably a little more than a actual rocket launch would have if it was realistic numbers. But I hope you can see that you can't just plug this in, the engine force, as Fnet, because there's also gravity pointing downward. And if you get in the habit of drawing a force diagram and labeling all forces, you will not make mistakes. If you get in the habit of trying to jump straight to some kind of equations without visualizing the picture, you might get most of them right, but every once in a while a mistake will slip in. So I highly recommend force diagram, label all your forces, then plug in the equation and the numbers. Alright, very last example here to help you see what's going on. Suppose a person is pushing a 25 kilogram box across the floor at a constant speed of 8 meters per second by exerting a force of 124 newtons. How much is the opposing friction force? So here we have a box, which is 25 kilograms. So we can draw our box, which is 25 kilograms, and we are pushing it. So we have F push, or F person on box, equals 124 newtons. Now it says we are going at constant speed. What does that mean? Constant speed, if you recall, means that the acceleration is 0, which means that the Fnet is 0. The only way the net force can be 0 is if there's something against pushing the other way. And this is, as it says, friction. So here we have force of friction. And because it doesn't say anything about any other forces, there shouldn't be anything else touching it. Friction is between the box and the ground, and the push is because of our hands. The force of friction should be opposing this, so it should also be 124 newtons, but it's backwards. So you might have been able to just look at it and be like, oh yeah, 124 newtons, no problem. But drawing this diagram is useful when the problems get more complicated. So let's look at part 2 to this problem. Suppose the box now goes onto a carpet floor where the friction force is doubled. So we still have the same box, 25 kilograms. How far does the box go if we're pushed with the same force? So we're still pushing, push, and you should always label your forces with a subscript so we know what's causing them. We're still pushing with 124 newtons, but now friction is bigger, force of friction is doubled, so doubled of 124 should be 248 newtons. Okay, how far does the box travel? How far does something travel is a question about motion. So we can break this problem in half. In the first half, we're going to be looking at forces and accelerations, and then in the second half, we'll be looking at the motion. So in the first half, we can use our normal equation, Fnet equals ma. This is your favorite one. You'll be using it in almost every problem. So we have a force forward of 124, and backward, or negative, this is backwards, negative, 248 equals, I'll put acceleration here, and I'll divide both sides by m, and the m was 25. So I subtract the two forces, then I divide by the mass, and let's see here, if we type this in our calculator, it's going to be a equals negative 4.96 meters per second squared. In this case, it's negative because it is going opposite of the way that we were pushing it, and it will be slowing down. So now we can set up our motion vi, vf, dt, a. Okay, what are we trying to find? We're trying to find how far it goes, which is distance, right? We know the initial velocity of the box is how fast we're pushing it, 8 meters per second. And it's going to come to rest, so v final should be 0 meters per second. And we know the acceleration is negative 4.96 meters per second squared. We don't know the time, and we don't really need the time. So we have to ask what equation relates vi, vf, d, and a. So we should have memorized these by now, but that's going to be vf squared equals vi squared plus 2ad. We are solving for d, so we want to algebraically solve this for d. So we got vf squared minus vi squared, and divided by 2a equals d. And now we can plug in our numbers. Vf is 0, so that's gone. So we have negative vi squared. Vi was 8, so I'll put that here. Negative 8 squared divided by 2 times a, and a was negative 4.96. So it's good because this negative will cancel with this negative. So ultimately we're going to go with 8 squared divided by 2 divided by 4.96. Type all that in your calculator, and we get 6.45 meters as the distance that the box will travel before it stops. And that's it. So I want to highly keep focusing on this idea of showing the force diagram, showing the Fnet equals ma, then getting the acceleration. And then to reiterate from chapter 3, when you're solving a problem about motion, list your variables, select an appropriate equation, rearrange the equation for the variable you want, plug in your numbers, and get an answer. For those of you that want to try to skip steps and get ahead, I can promise you that as the year goes on, you'll be more and more well rewarded for showing your work. It's a lot more clear for me as well when I try to grade it. So I hope this example's helped in this video, and good luck on the chapter 4 homework.